Good morning, everyone. Our team, Stark Industries, represented by Ishrat, Hunter, Manny, and Pooja, present to you today our planning process for the big design competition. First of all, just a quick overview of the competition. Here, as you see in figure 1, is the matrix arena. We have a 7 foot by 7 foot arena with four home zones represented by the different colors yellow, black, blue, and white. The starting zone, represented by the 30-inch rectangles in the figure, is where the machine is to be placed and launched, and the machine is to fit within a volume of 1 foot by 1.5 feet by 2 feet. Right in the middle, highlighted in red, is the EMP plus zone with the matrix in gray and Mr. Morpheus right in the middle. The objective of the competition is to score maximum points by accomplishing a set of tasks with our machines. The four task requirements for the big design competition include repelling the sentinel out of the home zone, collecting programming modules, taking the red pills, and capturing Morpheus. Here is a house of quality that provides a better understanding of the problem and what is required of the machine in the final competition. The most important engineering requirements, as shown in the House of Quality highlighted here in red, are the failure ratio and task accuracy requirements for each task. These include the positioning accuracy with respect to the beacons, task accuracy of the programming modules. We know that the programming modules should be moved into the home zone, and that could require as minimal effort as moving them half an inch within the home zone. We also have task accuracy for sentinel engagement, moving it out of the home zone and by how much. The most important customer requirements, as highlighted in the House of Quality, include repeatability of task completion. We want each task to be completed in a consistent manner. The machine should be robust to track variances and should perform consistently well despite changes in the different tracks of the arena. And the machine should be robust with competitive behavior and accurate with tasks.
Because the final machine will require multiple subsystems to operate simultaneously within the limited volume shown in Figure 3, volume constraint of machine, it is of highest importance that the subsystems do not interfere with one another. To solve this problem, each design challenge will be used as a stepping stone for the following challenge. In other words, each task will be completed with the volume of the total machine in mind. Also, each subsystem will be added to the machine used for the previous design challenge, such that the machine does not have to be rebuilt.
Shown in figure 4 is the function tree for the given task. The main subfunctions of the tree represent the five major subtasks that we need to perform, such as removing the sentinel from the home zone and placing the red pills into the red zones. Possibly the most important subfunctions are retrieving Morpheus and egressing from the EMP zone. And the hardest subfunction to develop will most likely be the one that brings Morpheus all the way back into Zion. Figure 5 shows the morph chart, corresponding to the lowest level of the function tree. The most important solutions to plan out will most likely be the ones that require the exertion of a force on an object, as the task restricts the amount of energy sources and thus their ideal distribution is crucial. Moving Morpheus into Zion will be a challenging engineering problem, not only because of the limitation of available forces, but also the volume limitation.
Moving on to the planning tools we use for our planning process, the first one here is the planning tree, where the large task of designing the matrix machine is decomposed into four manageable pieces. The first level of tasks, namely understanding the problem, developing concepts, building the various subsystems related to the four main tasks, and finalizing the design. As is highlighted here, finalizing the design is the most important task as it involves assembling and integrating all the subsystems into a final design that has to perform all the required tasks in the final competition.
The responsibility matrix allows each task to be assigned to the team member that would best complete said task. In order to do this, the responsibility is assigned according to academic background, previous design/building experience, and skills regarding machining and the tools provided. Doing so allows for increased group cohesiveness by increasing communication efficiency and time management. It also allows each task to be completed with the highest level of quality by assigning each task to the team member that is best suited for it.
Tasks are prioritized to prevent a shortage of human resources and time while keeping in mind the design process. By paying close attention to designs already in existence and spending more time in the beginning of the design phase studying rules, designs, and mechanisms, future renderings can then be made easier and production can proceed smoothly. Simultaneous task completion is also a key concept, as many design tools are best developed with others that are similar. This facilitates group understanding and saves time, as many tasks should be grouped together as seen in the prioritization matrix.
Figure 10 shows the Gantt chart. The major findings from the Gantt chart included the importance of simultaneous work on multiple tasks and also the importance of adhering to deadlines. That brings us to the end of this presentation. Thank you for watching.